All right, welcome back. Now we're going to start the organic chemistry section of this 2018 Chemistry 30 released items. Starting with question 23. Here is a picture of a branched hydrocarbon, and the question asks, the parent chain of the molecule, represented by the diagram above, is based on what? Nonane, octane, heptane, hexane. I see that that's trapped behind my face. There we go. There is a pretty big discrepancy between the difficulty of questions, I think. That's just the nature of any sort of exam. There's going to be easier questions, there's going to be harder questions. If you know organic naming rules and you understand that you can bend corners on a parent chain, you're trying to find the longest chain here. So don't just go here where that's 1, 2, 3, 4, 5, 6 carbons. You can turn corners, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons. This is our parent chain right here. And our parent chain has 9 carbons in it. We would number this parent chain if we were naming it. They're not asking us to name it from this side so that we get our branches or substituents on the lowest numbers. So this would be not bad practice to name it. If you are studying for your chemistry diploma, let's number it, let's name it. Here's our longest parent chain, and then we have methyl branches on carbons 3 and 6. So we would call this a 3, 3, 6 trimethyl, because there's 3 methyl groups. There's 9 carbons in the parent chain. That's nonane, which means that the parent chain here with its 9 carbons is a nonane. Let's look at another one. The herbicide 2,4-D is widely used for controlling broadleaf weeds. Its structure is shown in the line diagram below. Here is its structure. The herbicide 2,4-D can be classified as an blank organic compound with blank functional group. All right, this is another definitions one. If you understand the different categories of organic compounds, and this one's not too bad. First of all, we are separating them in column I as either aliphatic or aromatic. Aromatic means that you contain a benzene ring or a phenyl group. So the presence of this benzene ring here, which could also be drawn, maybe you've seen it drawn this way before, with 3 triple bonds that alternate. Could also be drawn that way. That's not the greatest benzene ring that anyone's ever drawn, but this makes it an aromatic. And then our functional group that is present. Now, you may initially be tempted to say that it is an ester because you see an oxygen right next to a double bonded carbon to an oxygen. But this is a carbon here. This here is a carbon, which means that this functional group is separated from this. This is not something you need to know for Chem 30. This is called an ether functional group. If it was an ester, then it would be O attached to the same carbon that the double bonded O is attached to. This is an ester. This is a different thing. And then this end here, that is a carboxylic acid. So the one that identifies those both correctly is D, an aromatic organic compound, and the functional group is the carboxylic acid. You could also say that you've got an alkyl halide, or I guess just a halide, a halogenated hydrocarbon. But the bigger functional group that's here is this carboxylic acid, and they don't give that as an option anyway. Going to the next page. Organic compounds and their possible uses. This one, if you've looked at the answer key at the beginning of the PDF that's linked in the description, you'll see that there's a lot of different answers for this question. You just have to link 2 organic compounds with their uses. There are many different possible combinations here that you'll have seen if you looked at the other one, at the key at the beginning. Octane, methane, methanol, ethanoic acid. You do not need to know every single one of these. One thing that might be helpful is that ethanoic acid has the common name vinegar. It's also known as acetic acid. Maybe you'll know about the uses of vinegar as a food preservative, but you didn't know that it was ethanoic acid. But if you drew this out, you'd see it's the same as acetic acid. And if you know the structure of that and vinegar, you'll know that it's used as a food preservative. I'm not sure why I started there. Octane, if you fill up your car at the gas station, then there's an octane rating attached to whatever type of gasoline you use. It's a fuel for vehicles if your vehicle doesn't run on diesel. Methane technically could also be used as a fuel for vehicles, and methanol is an additive that is sometimes used in fuel. Usually it's ethanol as a fuel additive. Methanol is used as antifreeze most often. I'm just drawing arrows that the ones that first came to me. Methane is also used as a fuel for home gas furnaces. That's a main component of natural gas. Usually it's methane and ethane. There's a lot of different combinations here. You could say 1, 5, 2, and 7. I'm just pointing out the ones that we've got highlighted here. 3, 8, 4, 6. But if you looked at the start of the key, they also accept 3, 5, 2, 5. There's lots of different combinations that are good for this question. Going to the next page. A student compiled the following data on a number of related organic compounds, and this data is going to be used for questions 25, 26, and numerical response question 10. You see that we have a bunch of alkyl halides with bromine as the halide substituent, and we have a bunch of alcohols, and then we are arranging them with a different location for the bromine and a different location for the hydroxyl group. Which of the following conclusions is a valid interpretation of the data above? Boiling point decreases as branching increases. Boiling point increases as the length of the parent chain decreases. Boiling point decreases as the number of carbon atoms increases. And boiling point increases as the functional group becomes less polar. All right. Based on this data, first of all, if you've looked at all of these compounds, maybe you've counted carbons, they all have 5 carbons. And so compounds 1, 2, and 3 are structural isomers of each other, as well as carbons 4, 5, 6 are structural isomers of each other. The highest boiling point for both of these is associated with the one that has the longest parent chain or the fewest branches. The lowest boiling point has the most branches. So right now, option A is looking pretty good. Boiling point decreases as branching increases. We'll see if we can rule out all of the other options, though. Boiling point increases as the length of the parent chain decreases. This is essentially saying boiling point increases as branching increases, since all of these have the same number of carbons. These two statements are mutually exclusive. So if we already said that A makes sense with this data, then B does not make sense with this data. C, boiling point decreases as the number of carbon atoms increases. Well, these all have 5 carbons. So this data above won't help you answer that question. And also, the boiling point will increase as the number of carbon atoms increases, just because you'll have more London dispersion forces as you increase the number of carbons in the molecule. D, boiling point increases as the functional group becomes less polar. Now, if you look at your periodic table and you compare the electronegativities of oxygen and bromine, this is our Chem 30 periodic table. Bromine has an electronegativity of 3, and oxygen has an electronegativity of 3.4. So the hydroxyl group will be more polar than the bromine. So I'm just going to write down here that OH is more polar, writing too fast, than bromine. And if you compare the alcohols to the alkyl halides, you'll see that they have a higher boiling point. So D is false because the more polar functional group makes a higher boiling point. So A is true. We already knew that A was true, but it's good practice to try and rule out the other options as well. Compound 2 can form when but2-ene reacts with blank in blank type of reaction. All right, so first let's draw but2-ene. But2-ene is a alkene with a double bond that starts on carbon 2. Here's our but2-ene here. And compound 2, let's also draw what compound 2 looks like. We can go back and take a look at it. Compound 2 is this one here, this 2-bromobutane, which will have our bromine attached right here. That also ostensibly means that if we've added a bromine here and we've gotten rid of this double bond, we must have added a hydrogen here. Because there's not a bromine shown here, but this carbon needs to have 4 bonds. So in order to get 4 bonds, it'll have to have 2 hydrogens here. There's already a hydrogen here, but now there'll be 2 hydrogens here because we've gotten rid of that double bond. If we're getting rid of a double bond, then usually it's a good sign that we have an addition reaction. But the thing that would add to this to create this compound would be hydrogen bromide, because the hydrogen would add to one side of the double bond and the bromine could add to the other side. If you reacted to pure bromine, then both of the carbons that were part of the double bond in this alkene would have a halogen attached to them. So instead, you would end up with a dibromoalkane and not just a bromoalkane. You would end up putting on 2 bromines. This is an addition reaction. You're adding to an alkene. It's not a substitution. A substitution reaction, you would be looking out for a second product. So you'd usually have 2 reactants, 2 products, and then you flip a functional group from your reactants to each other. But because you have 2 reactants in a single product, then this is an addition, and what's adding on either side of the double bond is a hydrogen and then a bromine. So D is our answer here. Use the following additional information to answer numerical response question 10. Here's a bunch of compounds that look somewhat similar to the compounds that were in the box on the previous page. The difference here is that these all have 6 carbons instead of 5. Using the solubility data in the table on the previous page, arrange the compounds numbered above in order of decreasing solubility in water. And then helpfully they've pointed out that decreasing means that we're starting with the most soluble, going to the least soluble. We'll follow the pattern that's on this page. The most soluble is the alcohol that has the most branches. This is our most soluble compound based on the data on this page. So, and our least soluble compound is going to be any of the alkyl halides. We've only got one alkyl halide here. This is our, this looks like it would be a 3-bromohexane. That's going to be our least soluble. That's the pattern that's shown on the previous page. And then our one that has the most branches will be our most soluble alcohol based on the data in the table on the previous page. It's again behind my face. There we go. So this has the most branches. It'll be the most soluble. Then one, where the hydroxyl group's in the middle of the chain, that was shown to be more soluble with this hydroxyl in the middle of the parent chain versus on the end of the parent chain. And this makes sense if you are thinking about the intermolecular forces involved in solubility. To be more soluble in water, you want to have the most polar hydrogen bonding interactions with water. This end of this long chain is hydrophobic. It's non-polar. It's not going to mix with the water. This end is hydrophilic. It will be able to make hydrogen bonds with water. But because you are spreading out those sides of the molecule, it'll be less soluble than something that has that hydroxyl group in the middle of the molecule to allow more water to surround it. Therefore, it's more soluble. And all of the alcohols are more soluble than the halogenated hydrocarbon because they're capable of not just having dipole-dipole interactions, but also hydrogen bonds, and that will make them more soluble in water. Myrcene, I think I'm pronouncing that right, is an example of a fragrant hydrocarbon. Myrcene is an alkene with a number of double bonds in its structure. When myrcene is reacted with excess hydrogen, H2, in the presence of a platinum catalyst, a decane isomer, C10H22, is produced. So if we react it, we're going to get a alkane. Now, we know that this is an alkane because it follows the general formula CnH2n plus 2. This is our general formula for an alkane. Myrcene's normal structure, C10H16, doesn't follow our normal rules for either alkynes or alkenes, where an alkene normally, if it just has a single double bond, is CnH2n, and an alkyne is CnH2n minus 2. But what we see in myrcene is we have actually, I'll write this here, for this myrcene molecule, which is in the formula C10H16, it really has the general formula CnH2n minus 4. Remember, an alkene compared to an alkane, you lose out on 2 hydrogens because you have a double bond. An alkyne, you lose out on 2 hydrogens because you have 4 hydrogens because you have a triple bond. Myrcene, you're losing out on 6 hydrogens because you must have, so here we have, I'm going to write here, we have 6 less hydrogens than the decane. Now, if you're reacting myrcene with hydrogen, then, and you can get all the way to the alkane, it means that this hydrogen could add onto those double bonds. So it must be full of just double bonds. And they tell us that it has a number of double bonds. It has no rings because the hydrogen gas would not be able to add on to a ring structure. The reason why I mentioned rings is because the alkene general formula is the same as our cycloalkane general formula. Cycloalkane, and our alkyne is the same as our cycloalkene general formula. What I mean to show by that is that every time you make a multiple bond, like a double bond, or every time you make a ring structure, you get 2 less hydrogens than the alkane with the same number of carbons. We have 6 less hydrogens, which means that we must have had 3 double bonds. And that is actually our answer to question 28, which I think makes more sense to attack first before we get to question 27. Now, if we have this formula, C10H16, then our isomers are going to need 3 multiple bonds or rings. Some combination of 3 multiple bonds or rings in order to get this number of hydrogens. We also need 10 carbons. But if you look through any of these structures, and I'm not going to count them all right now, all of these structures all have 10 carbons. So what's going to set them apart is whether or not they have the same number of hydrogens. And instead of drawing little hydrogens on here, I'm going to see if they fit this rule. They have to have 3 multiple bonds or rings. A, if you look at A, it's got a triple bond. That counts as 2 multiple bonds. And then we have a double bond. So this has 3 multiple bonds. So this would be an isomer. This would be an isomer, so A is not our answer. For B, we have 2 rings and a double bond, which means that we fit this 3 multiple bonds or rings. This would be an isomer. C has a benzene ring. Now the benzene ring acts as if it has 3 double bonds. But then you have 3 double bonds plus 1 ring, which means you would actually go over the number of multiple bonds and rings. So C would not be an isomer. This would actually, if you drew your hydrogens on this, this formula would actually be C10H14. So it is not a structural isomer. D, we'll check it, has 2 double bonds and a ring, so it fits that 3 multiple bonds or rings. D would be an isomer. Let's move to the next page, and that will be our last page on just pure organic. In order to prepare chemicals for industry, many organic compounds must be separated from their natural mixtures. Okay. Propane. Propane can be recovered from, and we got a couple of different organic materials. I'll just draw those first. I know I started reading. 1-chloropropane. 1-chloropropane would look like this. We're on carbon number 1. We have a chlorine. 1-chloropropene. So on the same carbon as our double bond, we will have a chlorine. Crude oil, I'm not going to draw a picture of that, and then asphalt. Propane. Propane would just be the pure alkane form of this halogenated alkane and halogenated alkene. Can be recovered from the organic material numbered what by the process numbered what. Okay, here's our processes that we have. We have fractional distillation and we have solvent extraction. You're not going to be able to use either of those reactions to change these into propane. These are methods of separating from a larger group of molecules. And usually this would happen from crude oil. So we're going to get our fuel hydrocarbons from crude oil by the process of fractional distillation. Propane has a very low boiling point, and so it will end up at the top of our fractional distillation fractionating tower where it's going to condense, and you can capture your light hydrocarbons. Propane reacts with chlorine gas in the presence of ultraviolet light in a type of reaction numbered what to produce hydrogen chloride gas, and the organic material numbered what. Okay, we have 2 products and we have 2 reactants. We have propane plus chlorine gas in the presence of UV light. What will we make? Well, if we have 2 things reacting and we end up with 2 products, they actually tell us what one of our products is. We end up with HBr, HCl, hydrogen chloride gas. We can put the little gas state there. Not a bad idea. And one of our products that has this propane skeleton. It's going to be either one of these. Well, really what we've done here is we have switched out a hydrogen from here. That's where the hydrogen had to come from. And we've lost a chlorine. We haven't made a double bond. If we've made a double bond, we'd actually end up with 2 hydrogen, because there's 2 hydrogen that would have to be let go if you were to make that double bond. And so we're just switching out a hydrogen that was present here. We're switching out a hydrogen that was present from the end. Alkanes reacting in the presence of UV light with a halogen is a substitution reaction. And so this is reaction number 8 is a substitution, and it would produce not a double bond with a chlorine, but just a halogenated alkane, which is going to be 1, our 1-chloropropane. Ethyl propionate can be formed by the reaction of which 2 things? I'm going to draw ethyl propionate just for some edification, but if you know your ester naming rules, then you'll know that the first word comes from our alcohol, and our second word comes from our carboxylic acid. Which means that the acid end of this molecule came from something that had 3 carbons. This is the acid end of the molecule. It's attached to the carbon that has the double bond, 1, 2, 3. And our alcohol end of the our ester has 2 carbons, 1, 2. The alcohol that would come in here had 2 carbons, that would have to be an ethanol, and our acid end had 3 carbons, 1, 2, 3, that would have to be a propanoic acid. Ethanol and propanoic acid. The alcohol and then our acid group. You don't actually have to draw the structure, you just have to know the ester naming rules to know which 2 molecules could have reacted. And I think that's the end of our pure organic, our pure organic questions. I think that there's a question later that requires some information on organic chemistry in the equilibrium section, but the next video will start on question 30 with some of the equilibrium stuff.